Up until now, I've been pretty sloppy about going back and forth between saying x and z as far as my horizontal scale when I'm talking about the normal distribution. Let's describe a little bit in more detail what I mean when I say x or z. So, when we're talking about a normal distribution, in general, we're going to define where we're talking about where we are on the scale. So if our normal distribution looks like this, where we are on the scale is generally somewhere on the x. We'll say where that is. That'll be x. So let's say we have a height. Let's say, I don't know, let's pretend 5'10" is average, I think. I think about 5'10" is about average for men. So let's say that would be 70 inches. I don't know what the standard deviation is going to be here, but let's pretend it's, I don't know, 3 inches? Sure, let's pretend it's 3 inches. So that means if we were to step over one standard deviation, so I'm saying mean is 70, and the standard deviation is 3. So in this instance, we would say if we have a mean of 70, we're right here in the middle. If we have a 73 inches, then you're one standard deviation to the right. If you're 76 inches, then you are 2 standard deviations to the right. If you're 67 inches, rather, then that's 1 standard deviation to the left. So these would all be values on our x scale. These are actually the measurements that are made. Redraw that x. So that's when we're talking about an x value on our normal distribution. We're talking about just whatever values are on the normal scale. Now overlay onto that a z-scale. The z-scale is referring to where we are, is the number of standard distributions away from the mean. Whenever we're talking about the z-score, then 0 is going to be right at the mean. It's always right in the middle. 1 is going to be 1 standard deviation above the mean. 2 is 2 standard deviations above the mean. -1 is 1 standard deviation below the mean. So these values that I've written here, their z-scores are, well, 70 has a z-score of 0, 73 has a z-score of 1, and so on. So this is essentially just an extra scale laid over the top of it, and it allows us to actually, what it really does is it allows us to look up these values in that standard normal distribution chart. Before the days where calculators were readily available, people would have to actually look these values up in the chart because it's a non-trivial question to find these areas. And so they're all found ahead of time, and then they're listed out in the chart, and you can just look them up as you need them. To go back and forth between z and x, in these instances it's rather easy because you can see 1 standard deviation above the mean is, well, 3 inches above 70. It's 73. But if we're talking about, okay, what if you're 71 inches? Where do you lie on the z-scale there? Or if you have a z-score of 1.2, where are you on the x scale? So as far as going back and forth between the z and the x scale, this little formula allows us to do that. So if we have our mean and our standard deviation, and we have our x value, we can use this to find the z value. If we have our mean, our standard deviation, and the z value, we can use it to find the x value. So you can kind of go either way with this. There's other things. If you know you want a particular x value to be a particular z-score, and maybe you're looking for what the mean needs to be or what the standard deviation needs to be, you can use this in other ways. Of course, if you have 3 of the 4 numbers, you can use that formula to find the remaining one. So importantly, when we're doing this, if I say the area underneath the curve between 67 inches and 73 inches, so if I'm talking about this area right here, this has to correspond to the area underneath the standard normal curve between a z-score of 2 and a z-score of 1. And that does end up happening here. So that's why we're able to use that standard normal chart. This is the whole point of the z-scale, so we can use that standard normal chart to look these things up. So let's just do a few examples. So first off, we have Dixie Office Supplies finds that its sales force drives an average of 1,200 miles per day per person, with a standard deviation of 150 miles. Assume that the number of miles driven by a salesperson is closely approximated by a normal distribution. Alright, so find the probability that a salesperson drives between 1,200 and 1,600 miles in a given month. So let's see, we're assuming this is a normal distribution, so I'll just draw a quick sketch up here. The mean is 1,200 miles. And we're trying to find the probability that a person drives between 1,200 and 1,600 miles. So let's see. The standard deviation is 150, so we're going to be a couple of standard deviations over to get to the 1,600 rather. So we're looking for what's the probability that they drive between these two values. In other words, what's the area underneath the curve between these? So first off, I'm going to look at if we wanted to do this on the calculator. This is going to be the easy way, the way that I generally recommend to do it. We're going to use normal CDF. We're going to say the lower bound is 1,200, the upper bound is 1,600, our mean is 1,200, and our standard deviation is 150. So exactly, you can see I'm just plugging the numbers in from this problem. And that's actually all we'll need to do here. So it is definitely an easier method to do this on the calculator. But I will look at how to do this, how we would do this. I'm not going to do the chart method for all of these problems, because I don't think it's a good idea to do that, actually. It's more work. So let's see, lower bound, upper bound, mean, and standard deviation. If you're entering these on the TI-36X Pro, it's going to be a slightly different order. You're going to do your mean, your standard deviation, then your upper bound, then lower bound, but hopefully you should be able to figure that out easily enough. Let's see, so we get 0.4962. That's the probability we're looking for. And yeah, that's all we would have to do if we were doing this on the calculator. If we're doing this on the chart, kind of a by hand method, then we'd first have to figure out what the z-scores. So this is the x. We'd have to figure out what the z-scores are for each of these. This one is easy. The z-score is just 0 because it's right at the mean. But this one is a little bit more complicated. We'd actually have to use this formula, this one up here. So z minus mu over, or sorry, x minus mu over sigma. So this would be 1,600 minus 1,200 over 150. So 400 divided by 150 should be divided by. We get 2.66 repeating. 2.67. I'm going to round that to the hundredths place because that's where, when we're looking values up in our chart, that's where we can find the values. All right, so 2.67. Let's see. I have a bunch of writing all over this, but that shouldn't be a big problem. 2.6 is this row right here. Just right on here. 7 is this column. This column here, right? Yes. So this row, this column, that's the value I'm looking for right there, the 0.9962. So the area to the left of this one is 0.9962. The area to the left of the mean is 0.5. It's right in the middle. And so to find the area between them, I'm going to do 0.9962 minus 0.5, which gives me 0.4962. So you can see I do get the same value. It's just a few additional steps. Find the probability that the salesperson drives more than 1,500 miles in a month. Let's see, 1,200 is right here. 1,500 is somewhere over here. It's supposed to be 1,500, not 1,800. We're trying to figure out that tail probability. I say it's a tail because it's kind of going off forever in one direction. Kind of looks like a tail. So finding the probability they drive more than that. This is a full 2 standard deviations above the mean. I don't expect this to be very much, but in any case, normal CDF. I think it is handy drawing up my little chart, even if I'm just going to be running normal CDF on the calculator, because it informs me as to what the lower bound and the upper bound are. You can see my region that I'm shading in is over here. This 1,500 is my left or my lower bound. My upper is going to be, well, 10 to the 99th. So when I'm doing this, my lower bound is 1,500, my upper bound is 10 to the 99th. My mean is 1,200. And my standard deviation is 150. All right. So we'll do normal CDF, 1500, 10 to the 99th, 1200, and 150. It is important that I put those in the correct order. I'm sure if you plugged some of these in a different order, you would have gotten a different number. So we get 0.0228. I'm just rounding this to 4 decimal places because I'm also going to do this one in the chart, and I want these numbers to look the same. This 1500, let's see, the z value of the 1500 is, well, 1500 minus 1200 over 150, whatever. It's 2 standard deviations above the mean. I actually happen to notice that because 2 standard deviations would be 300, and this is exactly 300 above the mean. But of course, 300 divided by 150 is 2, so that's another way to get that. So now I would want to look up to see what the area to the left of z equals 2 is in the chart. Oops. So z equals 2 in the chart is right here. It's 2.00. It's 0.9772. And this is the area to the left. So to find the area to the right, I'd want to use my complement rule to do 1 minus 0.9772. 1 minus 0.9772 gives us 0.0228. Alright, so like I said, I'm not going to be doing all of these using the chart, but there's a couple of them. I think it's good to see kind of how the chart would be used, even if you're doing this by the calculator.